Drones will become a central part of our lives. Drones are delivering packages, surveying cell phone towers, providing Wi-Fi, or fertilizing crops. Drones are assisting humans in dangerous work and serving as an entirely new computing platform, providing services that were previously non-existent. Airware is a company that is building a full-stack drone platform. In this episode, Buddy Michini takes us through the software architecture of a drone. Airware's drones have two operating systems, one for the real-time flight-critical aspects and one for application developers who want to build their own software for drones. I hope you enjoy this episode, Drones with Buddy Michini. DreamHost Cloud gives you fast virtual machines and storage for a low price. DreamHost Cloud brings infrastructure as a service together with 24/7 support and a great community. The DreamHost Cloud platform is all based on open source code that uses OpenStack and Ceph. Go to dreamhost.com/SE daily to deploy your application today and support Software Engineering Daily. With the easy-to-use UI, standard API, and a powerful SSD infrastructure backend, DreamHost Cloud has everything that you need to deploy and maintain your application. The billing for virtual machines is simple. Only 600 hours are billed max per VM per month with 100 gigabytes block storage included, and free bandwidth for a limited time. It's easy to try at dreamhost.com/SE daily. Deploy your application to DreamHost Cloud today. I know you've got that side project waiting for its deployment, and when you decide to deploy it, check out DreamHost at dreamhost.com/SE daily. Thanks to DreamHost for being a sponsor of Software Engineering Daily. Now let's get on with this episode. Buddy Michini is the CTO of Airware. Buddy, welcome to Software Engineering Daily.
Thanks very much. It's a pleasure to be here.
Yeah, it's great to have you. So let's start off with a simple question. What is a drone?
What is a drone? So a drone is an autonomous aerial vehicle. At least that's how we describe it. And the things that makes drones so useful is that you can put sensors on that platform to collect data from perspectives that are otherwise very hard to get to, either with someone on the ground or with a manned aircraft.
And you work at Airware. What are the goals of Airware?
At Airware, we're making a commercial drone platform. So previous to the sort of widespread proliferation of smaller drones, there were military drones, there were very large drones, and what we've seen is that the technology has reduced in size and commoditized. And what that's enabled is for drones to be used for civil and commercial purposes. However, they are very complex systems. There's lots of things to sort of worry about, not only technically, but also for things like compliance, regulatory, stuff like that. And so at Airware, we're making a full stack product for companies, in particular enterprises, to use drones for everyday business.
Okay, so what are some of those customer use cases for drones?
Yeah, so one that I can talk about that I think is pretty cool is with State Farm. So what we're doing with them is we want to put a drone in the hands of all of their property claims inspectors. And so right now, if you have roof damage, a claims adjuster will come to your house. They'll climb on the roof, take some measurements, identify some damage, and then hopefully write you a check for the damage to your property. What we're doing is sort of giving them this extra tool, this drone, that can much more quickly, easily, safely inspect the entire property, collect the similar data to what they would collect by climbing on the roof, and basically collect more data than that as well. So photos of the sort of entire property that can not only be used for damage inspection, but also things like underwriting, risk assessment, things like that.
Okay, so now that people have an idea for what the use cases are, what are the hardware requirements for a drone?
Yeah, so there are a few hardware requirements. So the basic components to a drone are the physical airframe, and that will typically obviously include motors and propellers. Those are the things that generate thrust. But also the motors need motor controllers. These are typically power electronics. Those all talk to an onboard computer, and that can either be an actual, sort of Linux-style computer or a microcontroller. And that's also interfacing with sensors. So there's several sensors on a drone. There are accelerometers, there are rate gyros, magnetometers. The drone typically has a GPS receiver so that it knows where it is in three-dimensional space. And so it uses all those things to generate an estimate of its state, where it is in the world, and then produce commands that then go back to the motors and control the vehicle in space.
Okay, and so Airware is building some of these hardware components. Other ones are more ones that Airware integrates with. What is the hardware that Airware is building?
Yeah, so at Airware, we build both first-party avionics hardware, but also integrate with third parties, as you said. So the avionics basically consist of the sort of things that I just described, which is the electronics that sort of form the brains of the drone, the autopilot, the sensors, all the software that fuses the sensors and does the flight control. And so the core of the Airware hardware platform is essentially an autopilot that can be integrated into vehicles.
Okay, so let's start to talk about the software. And I think one place to start is, what's the general interaction between the drone itself and the cloud service behind the drone? Before we delve into the specific components of each of those aspects of the drone application, just give me an idea of like the kind of the communication pattern between the drone and the cloud service.
Sure. So in the cloud, the process starts out in sort of the planning phase. And so there will be a request for data, essentially from either a customer or a service provider. And then the cloud can either in an automated way or a sort of semi-manual way, do things like create flight plans, create geofences that sort of constrain where the drone can go, run all of those through compliance checks for things like airspace, and then assign that sort of whole package to an operator. And so the data that comes from the cloud to the drone includes everything from an autonomous flight plan, which is sort of a fully mapped out 3D flight plan for the drone. It comes with operational constraints like geofences or maximum operating altitude, things like that. And it also can come with configurations for things like cameras and sensors that the drone needs to collect the data as it's flying autonomously. So we call that a flight package. It's everything that the drone is going to need to operate completely autonomously, and that's what comes down from the cloud to the drone. And I should say there's sort of an intermediate step where there's an operator user interface that can either run on a mobile device or a tablet computer that essentially takes that from the cloud and then interacts directly with the drone itself.
How would you say the interaction between the drone and the cloud servers, how does that compare to the client server interaction that we're more familiar with, like between a phone and the server?
Yeah, and so in many ways it's similar, but I'd say one of the things that's interesting about drone operations is that when the drone takes off, it needs to have everything, all of the information that it needs to actually complete the flight. Because one of the things on your cell phone, you've experienced a dropped call, or you're in some conditions you may lose data connection, and so the drone actually needs to know how to operate entirely autonomously, so that in the case that the link between the operator or by proxy the cloud to the drone is broken, either temporarily or for the duration of the flight, the drone needs to actually know what to do. So I'd say that's one of the sort of fundamental differences between how, say a smartphone might interact through a cellular network to the cloud with the drone, is that the drone needs to effectively download all the information it needs beforehand, and it needs to be able to operate entirely on its own.
So let's start to talk about some of the software that you use. What are the programming languages that you use on a drone?
Yeah, it's sort of full stack. So, from the bottom on the embedded processor, we're running a real-time operating system that's typically implemented in C or C++. And that's so. And for anything real-time that's running on an embedded system, that's pretty much the standard. Because of the predictability, speed, performance, type safety, memory safety, things like that. So for everything embedded, typically C, C++ is the standard. As you move up in the stack to the operator interface, we've used everything from C Sharp, Windows WPF. Python is very commonly used for a lot of the sort of data processing aspects on the ground station computer, and then also Java, Android, things like that. But on the drone itself, it's pretty squarely C and C++ for the actual microprocessor that's doing the real time state estimation and control. A lot of times there's also a application computer on the drone as well. And, just typically that's a Linux computer where you can then run, any host of languages that are running non-safety or non-flight critical operations for things like managing sensors and dealing with data in the air.
Right. And we'll get into that, the idea of those two operating systems that you have with the application framework side by side with this closed real-time operating system. Before we get to that, there's the heart of the communication in this drone system is this PubSub RPC middleware component. Can you explain how this communication layer works?
Sure, and there's actually a few different layers. There's sort of the safety critical embedded layer, and this is where threads are talking to each other on the real-time operating system. And there's also it's a modular avionics system, so there are also components that are networked over CAN, controller area network. And so there's sort of a low-level PubSub RPC layer that is running, where we need to guarantee delivery for things. We need to have some very strong notions of what the latency is going to be for some of these real-time control threads. That's low-level, and there are actually shockingly few libraries available for doing low-level PubSub RPC. And so a lot of that is kind of custom that we developed here at Airware. From the drone to the sort of outside world, there are lots of good frameworks that can be used for that come off the shelf. One good one is called Robot Operating System, which is primarily has clients in C++ and in Java, and typical PubSub RPC. And then there are some other more web-centric frameworks like Web Application Messaging Protocol or 0MQ. So once the data is sort of off the drone, it's really up to you to pick sort of the framework that makes the most sense, and there are a few that do. But on the drone itself, we're running a fairly custom middleware layer so that we can make guarantees about performance and safety.
And just to clarify, so this PubSub middleware layer, this is just for communication within the hardware on the drone itself. It's not for communication between the drone and the cloud. Is that right?
Yeah, on the embedded side. And so those are for things, the GPS module is physically separate from the actual autopilot. So the GPS module has its own embedded processor, as does the autopilot. It needs to send the data that it's getting from the GPS chipset to the autopilot so that it can process it. And so the PubSub RPC framework basically enables you to create topics. So in the case of GPS, there might be a GPS data topic. There might be a GPS status topic. And then within the topic, there's a structured message that has the fields that you would expect. And those messages are sent atomically, either thread to thread locally, or also, as I've mentioned, over a CAN network, where a lot of times it needs to be broken down into smaller packets, sent over the wire, and then reconstructed on the other end. But it's a framework that allows threads to talk to each other so that if I switch out the GPS module that we currently have with another one, the new one will just talk over that same topic, and I won't have to rewrite all of the software that talks to the GPS.
So this super low latency PubSub system, I think we've done a number of shows about PubSub systems built in Erlang or perhaps built in Java. But I think what you said was that there really is not anything super low latency built in C or C++ out there that you can just take off the shelf, right?
It's there are a few packages, but in terms of the memory size that they'll compile down to, the amount of RAM that they'll require, we found very few that were going to operate at a very low level with very tight constraints in memory and RAM.
Okay.
And so, but there are some. I mean, there are plenty of these packages in C and C++ that you can try to compile down. But then, when you put it on a processor that has memory that's in the kilobytes, and RAM that is also either in the kilobytes or low megabytes, it becomes very difficult to sort of guarantee the performance of those libraries.
Right. So if you're in a factory or if you're in a Wall Street trading company, you can have some super low latency C++ PubSub system that has totally different constraints than that of a drone.
Yeah, that's correct.
And so it sounds like your domain is extremely unique. Although it's kind of surprising that there hasn't been that requirement from a mobile operating system. Like I guess do mobile operating systems are there any that have that have a requirement for PubSub systems?
Well, even mobile operating systems these days are in a higher class of computation than the types of processors that we're using, and kind of the reason for that is that the timing for a lot of these things needs to be extremely precise and it needs to be guaranteed. Where if you move up in you can use a more powerful processor that typically comes along with sort of a larger abstraction between the machine layer and user space, which you do have more computation, but it's more difficult to get those guarantees in timing with something like a real-time Linux kernel. So I'd say even in mobile the processing is probably more plentiful than on the very small embedded processors that are typically used in drones. And even like in drones, even the TCP/IP stack is something that you have to optimize in terms of taking things out of it so that it will fit into the memory and and runtime complexity constraints. So things that we really take for granted at sort of the even the mobile layer, you assume that the TCP/IP stack is fully implemented. That's even something that you need to import as a library and oftentimes optimize to make it run efficiently.
Now, we've had a couple shows recently about unikernels, which are these library operating systems where you really pick and choose the things that you're going to have in your operating system based specifically on the requirements of the application. Have you looked at unikernels at all?
I have not, and I'm not familiar with them, but
okay.
It sounds very, very, very similar to what we actually do. So, for instance, we typically don't need USB device drivers for most of the embedded processors. And so that while that's something that you can compile in as a library, we typically will leave that out. We'll only bring in the drivers that we need, things like the CAN drivers, the most basic TCP/IP stack drivers, flash drivers for memory. So we kind of do. I think we kind of do what you're describing, maybe in a slightly more manual way, but it's certainly something that it sounds like is worth looking into.
Well, it's funny because the USB example is the canonical example that the unikernel guests gave, where they said, okay, if you're spinning up a Linux server in the cloud, you don't need a USB driver because even if you wanted to, you couldn't put anything in the USB port,
right? Yep.
Unless you want.
And there's tons of examples. Like we never need a display port or a display driver, for instance, on obviously on an autopilot on a drone,
right?
And so for the application computer, even we're using tools that will basically compile a minimum viable kernel that also I'm into constraints into the smallest Docker container that we can fit. But there are certainly optimizations that we've made, and I'm glad to hear that there are some tools that are starting to be developed that maybe automate that process a bit.
Yeah. Okay. So you mentioned this application framework. We should get into that. So this application framework is, to understand it, you need to understand that there's two operating systems on the drone, and the two operating systems communicate with one another. You have this closed real-time operating system that handles the flight critical aspects, and then you have this more open side of the application framework that is running some version of Linux with some various middleware. Is that an accurate description?
Yeah, that's correct, and we do that primarily for safety. So, on the closed side, we need to guarantee that the drone will not only operate safely, but it will also operate predictably, despite anything that the users or the developers in that system do. And then in between those two layers is a very well thought out sort of firewall, so to speak, where there is an interface between these two sort of domains, but it's very stringent and is very predictable. And then once you have that sort of safe side of the system and a robust firewall between the two, you can then let users kind of do whatever they want for the most part on the application side.
So it's interesting because as I was researching for this show and I was looking at this model you have for these two operating systems in order to support the user custom built applications they would want to run. It sounds like this is a problem that is, well, I shouldn't say a problem. It's a challenge that is going to have to be, people are going to have to develop more and more design patterns around it because as we get to self-driving cars and obviously there's cryptocurrency stuff where people are building applications on top of these frameworks or on top of these application systems where it's not like you're just building on a social network or some Twitter thing and you can really do whatever you want and have free reign. It's like you're really dealing with high sensitivity platforms. So when you were building this system of two operating systems where you have one where you kind of have it partitioned off and it's closed and there's not as much openness, and then you have this other operating system that interfaces with that and you have more freedom within that operating system. Was there best practices around this domain? Have people been thinking about this type of framework for a long time, or is this fairly new?
Oh, no, people have absolutely been thinking about it, and this is a concept that you'll find in lots of everyday devices. Your cell phone, as we were talking about earlier, actually has a very similar thing where there's a core that is related to primarily telephony that it has to, by government regulation, needs to be reliable. So if you need to make an emergency call on your cell phone, that system, needs to be certified to a higher standard, and that is essentially firewalled from then the application processor that will do things like run Android and all of that. Mm-hmm. And it's actually and it's a very interesting wall where there are some companies who are doing things with encryption where they're trying to push things down into that lower level processor to make, for instance, passwordless security more secure. But there, in cell phones, there is certainly this sort of division. In cars, it's the same way. So cars also use CAN buses for module-to-module communication. And there is a safety-critical CAN bus, and there's also a CAN bus that's used by things like the infotainment system, and the lighting systems and things like that. So certainly, this is a concept that has been around. I think one of the interesting things that makes it unique for drones is that there has to be an interface between the two sides, and that interface is fairly esoteric to autonomous flight. So we need to make an interface where applications can control the position and movement of the drone in three-dimensional space, because a lot of times the applications are putting the drone in a spot where it's going to collect the data that it needs to collect, but it's the onus is on the safety critical side to make sure that those sort of control commands are still safe. And so I think that's maybe the thing that makes it unique about drones. But even then, I mean, this is you'll find this in cars, in phones, in commercial aircraft. So the concept is fairly broad.
Mm. So what can I build with this framework that Airware presents to me that I can build my own applications with?
So what we're trying to enable, we think of the drone as a way to collect aerial data, and so and we want to we're taking care of as many of the underlying parts of the problem as possible, and again, not only at the actual physical drone layer, but all the way up through the planning and data analysis that happens in the cloud. But most of the applications that would, for instance, run on board an application computer that's on the drone would be related to, as I mentioned earlier, navigating the drone through space to put it in a position where it's collecting the data. where many of the tasks that we do are inspecting things. And so, for instance, inspecting a rooftop requires, moving the drone around to various areas of the rooftop, making sure that you are safely avoiding any obstacles that are in that environment. It's the same thing in when you're inspecting utility infrastructure. There are things like utility towers and power lines that oftentimes need to be navigated around in an intelligent way. And that navigation can sometimes be pre-programmed, but a lot of times that navigation requires real-time input from a sensor that is also on the drone. For instance, an array scanning LiDAR that you might find on a self-driving car. So one class of applications would be an application that takes data from those sensors, those real-time sensors that are giving information about what's around the drone. And then combining that with some type of plan for a thing that you might want to inspect, and then issuing commands to the drone so that it can navigate itself around the objects or infrastructure to be inspected to collect the data that you want to collect.
Wealthfront is an automated investing service that saves you time. As an engineer, your time is valuable. If you want to invest, but you don't want to spend significant time evaluating your portfolio and allocating assets, take a look at Wealthfront. Go to wealthfront.com/SEDaily to open an account today and get a special offer for Software Engineering Daily listeners. $15,000 managed for free when you open your account. With traditional investment services, there are many humans in the loop that are doing things that Wealthfront automates away. When you pay the commissions and account fees of these traditional investment services, you're paying for work that could be done by a computer. So don't pay commissions and account fees. Maximize your gains with Wealthfront's Set It and Forget It investment automation. Check out wealthfront.com/SEDaily. It would support Software Engineering Daily, and it would introduce you to the world of automated investing. Wealthfront.com/SEDaily. Thanks to Wealthfront for being a continued sponsor of the show. Now let's get on with the show. So what are how did you learn over time what things you could expose to the programmer and what, the application developer, and what things you had to restrict to the operating system that was more walled gardened off?
Sure. I mean, I think it's a combination of best practices, which there are. I mean, there are plenty of best practices around this in the form of industry group standards, obviously, a ton of literature. But then also, a lot, in my personal experience, a lot of it actually came from, my experience as a grad student, creating, building little flying robots and, flying them in an indoor lab setting. Through the sort of the course of getting a PhD in autonomy and AI, I slaved over, cried over a lot of robots that where I was testing high level applications. The research was mostly in autonomy and navigation and coordinated control with other vehicles, and that they would be issuing commands to these vehicles, and you start to get a sense for. You need to build a boundary around it so that the control application that you're testing can go completely haywire, but the drone itself will not crash, because if it crashes, that means that I need to spend the next 2 days putting it back together in the lab. So a lot of the experience, at least in my case, has come from hands-on experience with real small aerial robots in a research setting. And then combining that with, as I said, lots of the software standards that you would find in commercial autopilots, where there are some things that there are some threads that effectively cannot be interrupted. So you have sensor data coming in from, for instance, the accelerometer or the rate gyro. Those signals need to be numerically integrated at a certain time step, so that you can integrate the acceleration to get an estimate of velocity. You'll then integrate velocity to get an estimate of position. Those need to happen on a certain time step. If that delta t is different every time, the integration will be incorrect, and the drone's estimate of where it is in the world will be incorrect, which is a problem. And the same thing on the control side. So for a typical multi-rotor drone, this is the drone with, really simple, just four motors, four propellers, similar to, a DJI Phantom or lots of the consumer drones. That system from a dynamic perspective is completely unstable. So if one of those propellers is spinning just a little tiny bit faster than the other three, the vehicle will very quickly flip over. And so what that means is that the control, the rate at which I need to send different signals to those motors to keep the drone stabilized has to happen extremely quickly. And in often cases, that's thousands of times per second. And so, there are certainly some things where just to keep the drone stable and flying safely, that the timing of certain things cannot be interrupted. And so you kind of combine, some intuition and sort of hands-on experience with some of the software standards, and then some of just the very practical issues of maintaining the control of the system. And it starts to sort of paint a picture of what needs to be protected, and what can be sort of abstracted slightly further away from that safety critical core.
So let's talk some about this integration process, because you have this core flight system that can work with a variety of pieces of hardware, or I should say drones. What determines whether or not a specific drone is compatible with Airware's platform?
Yeah, generally, it depends on where the integration would take place. Most of the time, the thing that you're integrating will be something on the application side. So it will be a sensor. It might be an algorithm that runs on board. It might be some machine learning that's doing damage detection on images that are coming in from the camera. And so a lot of times it's software. And really that's just software that runs on the application computer. In terms of hardware, it's typically less common for to integrate safety critical hardware into a drone system. Typically, you want that hardware to be extremely well tested, and so mixing and matching the safety critical hardware is not something that's too common, just because of the amount of testing and validation that has to go through to give these sort of guarantees of system performance. That's less common, and I'd say most of what we've seen in terms of integrating third-party applications or third-party hardware typically comes in on the application side, where it's the same constraints as integrating something with a Linux computer. They're either plugging it in over USB or Ethernet, wrapping some middleware around the driver so that it's accessible from the other applications that are running.
Right. So, what about? Do you have to integrate with like sensors? Because there's a variety of hardware sensors that are on the market. Are the protocols for these different sensors standardized, or do you not need to worry about that?
Well, they're all different, and that's one of the reasons why a standardized middleware layer is so important. So between a Sony camera and a Nikon camera, the USB protocols for those cameras to control them programmatically are completely different. Oftentimes, they're almost always proprietary. They change very frequently, and so to maintain sort of a universal driver for every possible camera that you might plug in over USB to an application computer would be impossible. And so instead, the paradigm is to think about the services and the data that the camera might offer. So if I'm a camera, there will typically, there will be a service that's called Take Picture. There might be a service that, lists all of the pictures that are stored on the memory card. There might be a service that configures the aperture or the shutter speed of the camera. And so what you can do is come up with a list of the actual things that camera exposes to the world in terms of interactive services, but also data that it might be publishing. And you create middleware topics around those things. So you come up with remote procedure calls for any of these services. You come up with data topics for any of the data that's coming in or out. And then on the inside of that middleware is where you do all of the things that are specific to that camera. So that if I plug a Nikon camera in or a Sony camera in, there is a driver that's sitting underneath of this middleware module. But to the rest of the to the rest of the domain, they know all of the other apps that are on there, they just know that it's a camera, and they know that if they call the take picture service, it's going to take a picture. And so that's sort of the importance of middleware when you're integrating lots of different pieces of hardware and software. The same thing goes for software, by the way. There might be services, that take a photo and find and do harass detection on all of the corners. That might be a standardized thing that you want your software to be able to provide to other applications that are running on that same network. So that's where middleware comes in, and it's to sort of standardize the interfaces to these devices and pieces of software, because the actually underlying interfaces are just horrifically different in these cases.
Got it. So the middleware you use to impose a set of standards on the inputs that are viable for the platform itself, and this is a pattern that can apply to drones. It can apply to other things that have wide varieties of inputs.
Yeah, that's correct, and that's I mentioned earlier a system called Robot Operating System, and this is a framework that I would say has kind of revolutionized the way that real world robotics research is done, because once the academic community all started using Robot Operating System and then publishing their modules and their software to a common repository. Then, as a researcher, if I wanted to integrate, a 6 scanning LiDAR, and then also a SLAM algorithm, I don't actually need to write all the piping for those things. I just download the ROS drivers for those and run them. And now magically the LiDAR talks to the SLAM algorithm. And so that sort of happened, that actually came out of Willow Garage, which was a robotics company here in the Bay Area. But that's a good example of a middleware framework where it's kind of unifying things so that people don't have to spend as much time rewriting code, and can get to the end goal much faster.
Let's move up the stack a little bit. Well, maybe not move up the stack, but let's talk about computer vision. Is the state of computer vision a bottleneck to any of the potential applications of commercial drones?
Well, it depends on how you define bottleneck. I would say that there has been remarkable progress in computer vision for actually a lot of low-level things that are very applicable to drones. So you may have heard of Google has a project called Project Tango, I believe it's called, where they're taking real-time video feeds and oftentimes stereo or structured light. And they're fusing that with inertial sensors to essentially do visual inertial navigation and very precise navigation of the phone through space. So typically a drone would do this with GPS, but in situations where GPS might be obstructed or unavailable, there is actually enough information from a video camera and inertial sensors to reconstruct very accurately the position, velocity, and attitude of, in the case of Project Tango, a phone. And that relies on a lot of computer vision in terms of detecting features, doing odometry from frame to frame on a video. And not only does it require, computer vision algorithms, it also requires optimized algorithms that will be able to run quickly enough so that you can do this 50 times a second. So I'd say for many things, computer vision has actually, enabled not only drones, but robotics in general to do interesting things in navigation, in obstacle detection, and things like that.
Yeah, and one application of obstacle detection, I guess, would be coordinating different drones to avoid each other. Is that something you have to think about at Airware?
So not yet, and I'd say there's a big set of regulations that the FAA has just put out that are actually going live very soon, called the Part 107, and what that those regulations basically only permit operators to fly one drone at a time, and you're flying drones. You can't fly them over people or heavily populated areas. You have to fly them below a certain ceiling. So the regulations are essentially limiting the drone operations to not really yet necessitate drone to drone collision avoidance. I think down the road, once drones begin to proliferate, once they're sort of truly integrated into the national airspace system, the sense and avoid systems will become much more important. But I'd say for many commercial applications and applications that we're working on at Airware, that type of technology is not yet necessary. And so it's maybe down the road. It's an active area of research, certainly, in the academic community. So lots of interesting things happening, but not really necessary for commercial operations right now.
Right, and I think it's kind of like the kicking the can down the road sort of thing. It's the same thing they're doing with the self-driving trucks. I think they're talking about just giving them their own highways where they can be self-driving on, and then when they would get to an area that has roads with other people on them, then a driver has to get in the truck. So that they think of these ways of sandboxing the autonomous capabilities. It sounds like they're kind of doing something similar with drones, or at least analogous.
Yeah, and I think that's as a very practical technologist, that I think that is a smart way to go about gaining confidence in these autonomous systems. So instead of just releasing your sort of self-driving car out into the wild, and the same thing with drones, instead of just sort of releasing them into the national airspace with all the manned aircraft, it makes sense to start in a sandbox. You are proving out the technology, so the drones and the self-driving cars are in some cases driving autonomously, but maybe you're cheating for a few of the small aspects. Maybe it's sort of a closed course for autonomous trucks. For drones, maybe it's a very small sort of operational area that's closely monitored by an operator. So I think those are necessary incremental steps, and I think will not only build confidence in the system, but also start to gain public acceptance with a lot of this technology, where we can say, yeah, well, we've been operating these things and in a sandbox, sure, but we've been doing that for 10 years and we have all this data that points to how safe they are. It's much easier to then transition into the wider world if that's the path that you want to take.
Yeah. So speaking of computer vision, so there was this YouTube video I saw where you were talking about using change detection algorithms on images from drones. And I can imagine this being important if you have a drone that's flying over your crops, or flying over your cell towers, or flying over areas with certain types of foliage growing, where you would want to be able to diff new images against old images. What is the state of image processing when it comes to this change detection, and how well defined is this area? Do you have to roll anything on your own, or can you mostly take things off the shelf for change detection?
Yeah, and it really does depend on the type of data and the type of application. I would say that one of the reasons why this time series analysis has become much more interesting with aerial data is because drones can collect data much more frequently, and with less hassle than data may have been collected either manually by someone on the ground or from a manned aircraft. So drones make this data available on a much more frequent basis. And sometimes change detection really just means a slider between this is the photo before and this is the photo after. For some applications that may be enough. For other applications, you may want to be doing some type of analysis. You'd mentioned sort of vegetation, and vegetation encroachment is a big deal for a lot of the utility companies. And so that change detection might be sort of more volumetric in nature, where you're matching two data sets together and looking at how the volume of certain areas of those data sets have changed. Volumetrics are also really big in the sort of mining and quarrying industry, where the job is literally to move volumes of rock from a quarry or a mine, and make them available for construction. And for that, change detection does often involve looking at 3D models that the drone is able to produce. of a site over either two sort of time instances or even more than that, and seeing how the volumes of things like stockpiles or quarry faces have changed over time. So it's really there. I don't think that change detection itself is such a broad term. There are certainly some more advanced things detecting subtle damage or corrosion, for instance, on metal that is very common in lots of civil infrastructure. Some of those might involve some things like deep learning or more sophisticated image recognition. But I think lots of times change detection is really, is maybe more straightforward. And I think the thing that has limited the application of it has been the data source. And that's one of the things that drones are starting to change.
You mentioned the Quarry analysis thing, and I had not known about this job until I watched some of the YouTube videos about Airware. This is a job where you have like a mine or a quarry, and you have a big pile of whatever is being taken out of the quarry, and there is a job that some worker is employed to do where the worker walks around and looks at the pile of stuff that has accumulated out of the mine and I guess documents it. And this is one of these jobs where I'm like, oh my gosh, I'm so glad this is going to be automated.
Yeah. There's lots of jobs like that. And it this is an example of where drones have the potential to really revolutionize the way things are done. So, previously, to do sort of a full volumetric analysis of a mine or quarry, oftentimes, you have people who are with ground-based surveying devices that are walking around. It takes a long time. A lot of times it's unsafe because they're these people physically have to put themselves in in places where they can take measurements. With from the aerial perspective, and especially sort of the low altitude perspective of a drone, you can capture a lot of data that can be turned into much more accurate volumetric and 3D models of that same place. And it takes much less time. It's obviously a lot safer. And as I said, if you can do it more frequently, you can that data is much more powerful when you do the time series analysis. And then you can also it's also more accessible. So one of the other big parts of what we're delivering at Airware is a cloud platform that will not only run the data through an analytics pipeline, but also present it to users in a way that is more accessible than for instance a CAD file that may have been generated from one of those surveys that would then create an information bottleneck. So not only collecting the data more quickly, more frequently, but also making it more accessible is I think something that not only in mines and quarries but for many industries will sort of fundamentally change the way that day-to-day operations work.
So we've done all these shows about various software companies, and we often discuss their continuous deployment strategies, continuous delivery. That is not, I imagine, the case with drone software. You can't just like push a change to drone software to the pipeline and have some easy automated test. It's more, there is manual testing, I'm guessing, and by manual we really mean manual testing. Yeah. What is the cycle for testing updates to these drones?
Yeah, certainly. I mean, it is not an industry where you can move fast and break things, especially with the flight critical software. But believe it or not, there are lots and lots of automated tests that we do before that software is ever flown on an actual drone. And the flying is almost the last step, and it's more of a verification step than an actual test step. So to kind of take you through it, there's lots of different levels of testing. There are obviously unit tests that are testing small portions of code. And you sort of step up the level of integration with that code and the other modules that it interacts with. So there are level 1 tests that may be sort of integrations from thread to thread. There as you go up, you start to test maybe then 2 pieces of hardware that are talking to each other. So at Airware, if you're ever here, it's really fun because there's lots and lots of hardware sort of all out everywhere, and a lot of that hardware are these automated test rigs, where we can essentially flash, candidate releases, or even just intermediate development branches, to an actual hardware system that is representative of what is in the drone itself, and then run a series of tests on that hardware. One of the core concepts in testing lots of different sort of robotic systems, but in particular autopilot systems, is something called a hardware in the loop simulator. And what this does is you run your actual code on the actual target hardware on the autopilot, but you'll send commands that would go to real motors on a real drone, but instead you take those commands and you feed them into a simulation that's running alongside the test. And it's actually a physics simulation. That physics simulation then generates the data that your sensors would report if this was the real world and not a simulation. And that data gets sent seamlessly back into the hardware system. So your software actually does not know the difference. It doesn't know that it's not flying a real aircraft, but it is in fact a software simulation. So this is called a hardware in the loop simulator. And this is one of the key components that we can do very extensive testing and automated testing using a hill sim, and we have a very high degree of confidence that the software is going to perform as intended by the time we get it out to the field. So yeah, the hands-on testing is kind of the last step, but it certainly is an important step.
So is the software development lifecycle a little slower, a little more constrained than somebody building a web app, for example?
On the drone software side, it is a little bit slower. The testing necessarily needs to be more comprehensive. The actual development needs to be more disciplined, in terms of making sure that interfaces aren't broken, making sure there aren't unintended consequences, to the commit that you're about to push. I think the thing that may slow it down is all these levels of testing that sort of need to happen in sequence in order to build confidence. I'd say though, on the for the other half of what Airware does, which is all in the cloud, we have a very modern, agile, continuous release, continuous delivery development philosophy where we are able to move a little bit faster.
Right. So this is the whole data engineering side that we haven't really had a chance to discuss. All this data that's being gathered by the drones, you have a platform for dealing with it, processing it, a user platform. And we could discuss that, but we're running low on time. I want to just discuss a few things that are more specific to drones. What's the state of drone regulation in the United States, and how does that affect how you write software?
Yeah, so right now, and I mentioned earlier, but the FAA is getting ready to release what is sometimes termed the Small Unmanned Aircraft Rule. More technically, this is called Part 107, and that is going to enable a single operator to operate a drone that is below in a certain size class, so less than 55 pounds. Operate within line of sight, so you need to be able to see the drone at all times. Operate it, not over people, and not over non-participating structures, and some common sense things like it needs to be operated during daylight hours only. So that, and that's the regulation that is, I think, literally the next few days getting ready to be rolled out. And so, and which is really neat because that also comes along with a certification program for drone operators, which there has never been before in a scalable way. So starting very soon, you will be able to study and take a test to become a Part 107 drone operator, which is really exciting. As I described those, you can get the sense for what some of the limitations are. For many applications, you may want to fly beyond visual line of sight. If you want to, for instance, inspect a pipeline, you may want to operate larger aircraft. You may want to operate with multiple operators that you may be passing the drone off to, maybe multiple drones that are operating at the same time. So what the FAA has, what they've done is very smart in the sense that they're starting with sort of limited operations and feeling that out. There are also waivers. So if you do want to do beyond visual line of sight, you can work with the FAA, provide them data to say that your system is safe and reliable, and your operations, and they can issue you a waiver to say, okay, you're now allowed to operate beyond line of sight, but with under these certain restrictions. So that's kind of the current state of drone operations, and this is kind of the way it has been in Europe and Canada, for instance, for a few years now.
Do you have any knowledge to how your software architecture for your drones compares to that of Amazon and Google? Like, I'm very curious how the drone software architecture ecosystem is developing, how open it is, how much discussion there is.
Yeah, I think it's a little bit interesting because for a lot of the sort of flight software, a lot of that heritage comes from autopilots that you would find in manned aircraft, and for those, there's a very stringent set of software development guidelines. One example, there's a standard called DO 178 that has 5 different levels of safety, where DO, an autopilot that controls the 737 aircraft, that you fly across the country, might be DO 178 level B, which is very stringent. Now for drones, the risk profile is much different, and so and again, the regulations can impose these restrictions that make the risk of damage to persons or property much less. And so, and accordingly, the software standards are sort of less stringent. So there's a heritage that comes from sort of unmanned, from manned aviation and autopilots. But at the same time, there's, for instance, open source autopilot projects, where either hobbyists or people who are really interested in this as a technical area can kind of collaborate as a community and make iterative software that for what we're doing here, we need to strike a balance between agility of development, but also of safety. So it is interesting, but there certainly are open source autopilot projects that fairly large communities have sort of piled onto and developed and tested.
Okay, but it sounds like there's not much openness to the Amazon or Google corporate programs. Those are more insular.
I think what ultimately happens is that for the lower level that you go on the software, the sort of more esoteric that software becomes to the specific hardware configuration or the specific application, or the specific vehicle even that that you're sort of putting that hardware on. So I think that inevitably happens, and so it is a little bit more difficult the lower you go to kind of share things. But there are certainly best practices and lots of common knowledge in terms of how these systems should be designed, at least.
Yeah. Okay. Well, Buddy Michini, thanks for coming on the show and taking the time. This has been a great conversation. I'm glad we can do some coverage on drones on Software Engineering Daily.
Yeah, thank you so much. It's been a pleasure, and I really love the podcast. I enjoyed the conversation on AI. And yeah, which was fantastic, and I think definitely applicable to drones. So yeah, thanks for having me. I really enjoyed it.
Thanks to Symfano for sponsoring Software Engineering Daily. Symfano is a custom engineering shop where senior engineers tackle big tech challenges while learning from each other. Check it out at symfano.com/sedaily. That's symphono.com/sedaily. Thanks again, Symfano.
Wow.